Okay, thanks everybody again. I'm Kyohei Mukaida from Keck in Japan. Today I'm going to tell you about my work in collaboration with Keisuke Harigaya and Masaki Yamada. And when this research actually started when I was PhD course, and the topic is related to the question of how did the hot universe start. Okay, anyway, let me start with the brief introduction. I haven't imagined that I get such a kind introduction for me, so I just prepared this slide because to self-introduce me. This is my name in Chinese character. Well, the meaning is that in front of the rice field, enjoy the peace. I like this day very much, peaceful name. And I'm a father of 3 children. And as introduced, I spent most of the time staying in university around Tokyo area and did my postdocs around European area, and I moved back to Kyohei Tsukuba from 2021. My main research interest is in the play of particle physics and cosmology, and this one, okay, difficult to use. So this one is the standard model. So there are many particle like electron, muon, tauon, the neutrinos, and quarks, and the electric gauge bosons, gluons, and also Higgs boson. After the discovery of Higgs boson, we know that the standard model of particle physics is established. But however, once you come to apply the standard model to the understanding of a universe, it is known that standard model is not enough. So this is the well-known picture describing the time evolution of universe that is going from left to right, the time passes through, and this is the current universe. Okay? If you're going back to the history of the universe, since our universe is now expanding, it means that the previous universe was extremely hot. So the hot universe, it means that you're probing the high energy physics, but because of the measurement of CMB and other observation, cosmological observation tells you that standard model is not enough. So I'm interested in probing high energy physics by using the measurement of the early universe model. And the key question is that what is the origin of inflation, how did the hot universe begin, and what is dark matter and how they were generated in the early universe, and what leads to the baryon asymmetry of the universe, and so on. These are the key questions I'm interested in. And today's topic is one of the key questions. I said that the universe was expanding, so it means that the universe was extremely hot. So let me briefly recap why we think the universe was extremely hot. So the reason is that from the observation of many cosmological observations, one of a well-known one is the Hubble's law, is that we know that the universe is everywhere of the universe is expanding, and in particular that expansion can be characterized by the adiabatic expansion. Okay. The basic reason is that why we can regard the cosmic expansion as an adiabatic expansion is simply because the gravity is extremely weak. So you can compare the expansion rate. Suppose that your universe is dominated by the relativistic particle, and then the only scale you could imagine is the energy density or temperature. So energy density should be temperature to the force. And Einstein equation tells you that the expansion rate, which is denoted by h, the hyperparameter is proportional to the energy density, square root of the energy density. So it means that the expansion rate is proportional to the temperature square divided by the Planck scale. And compare this expansion rate with the typical interaction rate of the particle in the plasma. That should be proportional to the temperature times some coupling constant. And for the reasonable size of the coupling, like gauge interaction, alpha would be 0.1. And assuming that your universe, the temperature of the universe is smaller than 10 to the 16 GeV, you can show that in the most interaction, expansion rate is much, much bigger than typical interaction rate. This nothing but reflects the fact that the gravity is extremely weak compared to the fundamental interaction. So that's why we can think of the cosmic expansion as an adiabatic expansion. So that's why we can define the temperature, because we can use the notion of thermodynamics. And this kind of theoretical or intuitive understanding can be tested or already tested by the observation. The one well-known one is the cosmic microwave background, and this horizontal line is basically frequency and momentum, in the frequency or momentum divided by 2 pi, and this is intensity of the photon. And you can see that this blue solid curve is the Planck distribution, and red dot point is the coordinator. So you can see that this distribution is perfectly consistent with the Planck distribution with a temperature of almost 3 Kelvin. And this is almost the same for everywhere, up to tiny fluctuation, whose amount is 10 to the minus 5. So that is one observation, one key clue that our universe was extremely hot. The another one is Big Bang nucleosynthesis, which is a bit indirect, but however, it is also consistent with observed abundance of light elements like helium-4, deuterium, and also CMB also depends on the number of the excess of baryon to the anti-baryon, and CMB just putting us to this narrow band here, and this yellow box is the prediction of Big Bang nucleosynthesis. You can see that both two observations that are completely independent but still perfectly consistent with each other. So this means that the generation of light elements is also consistent with the indication that our universe was extremely hot. So from these observations, it's regarded as a success of Big Bang cosmology, which is based on the fact that our universe was extremely hot. But however, as you know, Big Bang cosmology has very difficult problems, or contains very difficult problems. One is horizon problem, denoted by this figure. So we observed that the almost entire sky, the same temperature, but for no reason. Okay. If we are kind of observing some region A, some region B with the same temperature, but if they don't talk to each other at all throughout the entire history of the universe, then it is no reason to believe that they have the same temperature. So that is the horizon problem. And another problem is a bit technical, but there's a flatness problem that our universe was very close to the zero curvature state. So this is again we need a very, very fine-tuned initial condition, otherwise curvature easily dominates the energy component of the universe. So that is another question. And both of them can be solved by assuming cosmic inflation. And that's why now standard cosmology, the cosmic inflation has now become a standard, the purge, essential purge of the standard cosmology. So assuming that some epoch before this ordinary universe, the so-called inflation, which is characterized by the constant expansion rate, almost constant expansion rate of the universe. So hyperparameter is the constant. So if the expansion rate of the constant, it means that the universe is exponentially expanding because the rate is constant. So this is nothing but the accelerated expansion in time. So if you have this kind of epoch in the early state of the universe, then inflation can bring these 2 points to the far away, which seemingly cannot communicate with each other if you just look at this time. But however, you can have causal contact before inflation, for instance. So that's why that's one way to solve the horizon problem. And the flatness problem is the same way. So if you have exponential expansion, any curvature would be just diluted. So you can essentially flatten the universe by the cosmic accelerated expansion. So that's the success of inflation. So it solves the horizon and flatness problem. And not only that, actually I didn't explain, but they can also explain the tiny fluctuation of temperature of the order of 10 to the minus 5 observed by the cosmic microwave background. So they not only solve the problem, but also provide the origin of the fluctuation and the ultimate structure of the universe we observed today. But however, this nice idea brings us to another problem, which is the empty universe problem. So inflation is an accelerated expansion of the universe, so it completely dilutes everything, include ourselves, standard model particles, baryons, and also dark matter. Nothing is left after inflation because they completely dilute. But as I said, to explain BDN and see cosmic microwave background observation, we have to create a hot universe with high temperature. And also, if we have to create dark matter, which is indicated by many of the measurements including CMB, and antimatter asymmetry, and otherwise we could not exist. And that is also one of the prediction of the observation, and also one of the prediction of Bitcoin nucleosynthesis. We need tiny baryon asymmetry. So everything should be produced after inflation, because inflation dilutes everything. And that is the problem of reheating, so-called reheating. Historically, we call reheating, but there is actually, well, nowadays it is not reheating, probably the proper name would be heating, just heating, but for some historical reason we call it reheating. And that phase transition, or kind of phase transition from the inflationary phase to the hot universe phase, and we need to understand, we need to fill in the gap between these two states, otherwise we cannot explain current universe, and also understanding that process could solve certain problem of the standard model particle physics, because during the course of the reheating, maybe we can generate a baryon symmetry or dark matter or whatever. Yeah. So that's the reason reheating is kind of interesting topic. And that is one thing, that is the main topic that I would like to focus on. Okay, so let me explain the intuitive understanding of reheating by using this cartoon. So during the inflation, this is the phi, so-called inflaton. We call it inflaton. Inflaton, and the horizontal axis is the field, and the vertical axis is the potential of the inflaton. And during the inflation, this blue circle is the inflaton field value. They are basically slowly rolling down potential. So then you have the constant energy density during that regime, and that almost constant energy can be used to the accelerated expansion. So this is the phase of the reheating, and there is no particle because of the exponential expansion. But after reheating, we have the inflaton field start to oscillate around its minimum like this. And in this epoch, if you have some, we should have some coupling between the inflaton field and the other field, including standard model particles. This is the Lagrangian, and other maybe beyond standard model particles, and they are generated in this inflaton oscillation period. So this is the phase of the reheating. And at some point, inflaton completely loses its energy, and all the energy is converted to standard model particles and other particles, and that is the beginning of the hot universe. So this is more physical picture or intuitive picture. So the horizontal axis is the time, and the vertical axis is the energy density of the various quantities. This black solid line is the energy density of inflaton. During inflation, it's almost constant, but after inflation ends, it starts to oscillate around its minimum. Then because of the cosmic expansion dilutes the energy density of inflaton. So that's why it becomes smaller and smaller as time goes on. And this A is the scale factor, which characterizes the expansion rate of the three-dimensional box. Okay, and this brown solid line describing the energy density of relativistic particles, radiation, and they get generated after inflation. And at some point, when the time becomes comparable to the inflaton decay rate, then the inflaton completely decays and radiation-dominated era starts. And that, assuming that the radiation is already thermalized at that epoch, we can define the effective temperature around here, which is referred to as reheating temperature. And after that, the universe is the hot universe starts. So that is the beginning of the hot universe. And this process of reheating and thermalization strongly influences dark matter production, baryogenesis, and also successful explanation of the hot universe. So understanding that process is quite interesting. And let me explain in the more detail about this process of reheating. But before going to that direction, I have to mention one thing. So in order to create the standard model and beyond standard model particle from the inflaton field, we need some interaction between standard model and beyond standard model particle with the inflaton, since otherwise inflaton energy density cannot be converted to the relativistic particles. So there is no constraint. Well, it's no constraint is too much, but almost no constraint. There is a certain constraint, but very, very big. And we can consider many models. But one theoretical concern is that once you introduce this coupling, then because of the radiative correction becomes from the standard model loop and other vertical loop, inflaton potential gets disturbed or get modified. But to have successful inflation, as I said, we need this plateau region of the potential, since otherwise inflation cannot be supported. So theoretically, a well-motivated candidate is that the one is considering small coupling between these two operators, like Planck suppressed operator, so something like this. Phi is inflaton, and Planck is the Planck scale 10 to the 18 GeV, and F mu nu is some gauge field strength, okay? Gauge kinetic field. And another one is dimension 6 operator like this. But anyway, these couplings are very small because inflaton mass is much smaller than the Planck scale, so this is very, very small number. So in this case, the standard model loop corrections are suppressed, so maybe we can support the flatness potential. The other direction is to consider the shift symmetric coupling between inflaton and standard model particle, like Chern-Simons coupling, but I will not go into that direction. I will focus on the small coupling, such as Planck suppressed operator. So let me briefly explain what to expect in this case. So initially, inflaton is regarded as a kind of both condensates like this. So this circle is the de Broglie wavelength of inflaton 1 over characterized by the 1 over inflaton mass. So we have many particles inside this de Broglie wavelength. It means that inflaton can be regarded as a certain both condensate. But because of the cosmic expansion, the number density gets diluted, and at some point, situation becomes like this. So inside the de Broglie wavelength, typical number of inflaton becomes much less than unity. So now, inflaton can be regarded pretty much as an isolated particle, set of isolated non-relativistic particles, and this condition is realized if this is satisfied. This first inequality means that inflaton is not yet completely decayed. The another one is automatically satisfied if you consider Planck suppressed operator, small coupling. So in the case of Planck suppressed decay, the situation automatically approaches to this regime. And now, at this point, inflaton, of course, is not yet completely decayed, but the decay process is probabilistic. So some amount of inflaton particle starts to decay and produce standard model particle. For instance, if you have two-body decay of inflaton into the standard model particle get generated in a back-to-back, and they are pumping up very high energy standard model particles whose energy is of the order of inflaton mass. So, and then the produced standard model particle get interact with among themselves, and they form the thermal plasma. So this is the typical picture how you generate the hot universe in this kind of scenarios. So the last situation we have to consider is like this. So you have thermal plasma which is generated because of the previously decayed inflaton particle, and at some point when inflaton particle come to decay, then the standard model particle is not interacting with among these different points of the decay, rather interact with the background thermal plasma. Okay, that process becomes dominant. And this process, this is regarded as in-medium cascades of the high energy particles, and that becomes the bottleneck of the thermalization. And this process is actually closely related to the physics of the heavy ion collisions, and well studied. And we can use that techniques to analyze the system. So let me going into the details by using a couple of minutes. And right, so what we have to understand to understand the reheating process of this type of model, then we have to understand the rate of the standard model particle whose momentum is of the order of inflaton mass. They interact with the plasma and how they lose its energy into the plasma. So this is the bottleneck process of the thermalization in this case. So, but in order to understand the process, we have to consider it is not just a medium cascade, because the incoming energy of this particle is of the order of inflaton mass, which is much larger than the background temperature. So in this case, we have to worry about the destructive interference effect, which is known as the Landau-Pomeranchik-Migdal effect, known in the context of the high energy QED. And suppose that this inflaton particle interact with the plasma with some gauge interaction, and they would split into two particles. But since this momentum is super large, then they are not far away. So we have to take into account the interference effect of these two particles. And this actually suppresses the rate. So what you have to actually compute is the multi-scattering processes, and this gives you the dominant effect. And that can be understood by just looking at this interaction rate, gamma splitting rate, and the first alpha square temperature, which is nothing but the typical scattering rate of the relativistic plasma, and alpha is the fine structure constant gauge coupling of the plasma. But you have to multiply this factor, so-called LPM suppression factor, and you can see that if the inflaton mass is much, much larger than temperature, M5 is much, much larger than temperature, then this factor dramatically suppresses the splitting rate, and for this reason, this process becomes the bottleneck of the simulation. So this is a technical slide. So basically what you have to do is to take this effect into account and write down the Boltzmann equation of the subspace standard model, and plug in the source term from the inflaton decay and solve the Boltzmann equation numerically. That you have to do. I just skipped the details, but what we have included is all the standard molecular interaction and Tokyo color. So this is the result, one of the key results, so which is related to the previous instantaneous simulation approximation and our contribution. So if you assume instantaneous simulation, it means that whenever inflaton decays into any particle, decays sample instantaneously. So in this case, this dashed line and dotted, the solid line describes the RE time, some RE term, some light time, and this is the phase space distribution, and this is the momentum, and this is the phase space of momentum P, and this is both of them a thermal distribution for the instantaneous simulation approximation. And also, you can see that if you go to the earlier time, the effective temperature of that distribution is larger. So from this, if you assume instantaneous simulation, you can estimate the maximum temperature of the plasma, and which is much, much larger than reheating temperature. That is well known in some papers. But once you have taken this finite time simulation effect into account, then this picture is no longer correct, because simulation has some bottleneck process. It takes some time to get stabilized. So in this case, then this is the distribution again. The horizontal axis is the momentum, and vertical axis is the phase space distribution. And you have two contributions: high energy tail, and thermal distribution. And for the early time distribution, you already have certain thermal distribution, but however, most of the energy is dominated by the high energy component, because the decay product is not yet sufficiently interact with the plasma, so they don't deposit free the energy into the thermal plasma. But at some point, they free deposit the thermal energy, their high energy particles deposit their energy into the thermal plasma. Then the thermal distribution reaches the maximal temperature. So you can compare this finite time simulation with the instantaneous simulation, and you can see that order of magnitude suppression in the maximal temperature. And also, in the previous paper, we focused on the inflaton dominantly decay into two gluons. Of course, there is no restriction, so you can consider other decay channels, like inflaton can couple to the other standard model, Higgs, electron, whatever. And this is the result for the inflaton glue channel. And now we are focusing on this high energy tail, just high energy tail. I completely dropped this thermal tail because this is well understood. And I also multiply momentum of P to the 7/2 to cancel out this universal power or behavior. Now, this is the inflaton mass. So initially, this purple dotted dashed line is the gluon distribution, and multiplied by the momentum to the 7/2 factor. And if this becomes plateau, it means that it reaches this asymptotic power behavior. Okay? So if you start from gluon always dominates the energy, and at some point, a different color indicates different standard wave particles, but all of them approach certain universal asymptotic behavior. An interesting point is that this universality at the low momentum is actually insensitive to the insensitive to the inflaton decay channel. For instance, you can consider inflaton Higgs to Higgs. initially, of course, right after the decay, all the energy is carried by Higgs particle, but however, Higgs particle can also interact with the background plasma, and they can emit other standard model particle. In this way, after multiple splitting of the individual particles, they approach is the same, exactly the same distribution. So this is kind of regarding the universality in the non-equivalent steady state. So you can think many different inflaton couplings like quark doublet, top quark, right-handed electron, left-handed electron, up and down quark, U1 hypergauge boson, SU2 gauge boson, Higgs gluon, everything just approaches to the universal distribution. So this means that this type of reheating, although it has model dependence between the inflaton coupling, how the inflaton coupled to the other standard model particles, but however, the distribution has universality. So you can have kind of model independent predictions of this type of reheating process. So of course, you can use this distribution function to produce dark matter, and you can have kind of universal dark matter production process if you have this type of interaction. And also, this process is non-equivalent, so you can also produce the lepton asymmetry from this cascading decay of the high energy particles. Okay, so let me conclude my talk. So, in medium cascades becomes the bottleneck of the start of the hot universe. In the case where, for a certain class of inflation model, where inflaton couples to the other particle, coupling of inflaton to the other particle is weak, such as Planck surface operators. And in this case, the maximum temperature is dramatically suppressed, order of magnitude suppression, because of the random Lagrange Miller effect. And once you specify the model, or like a standard model, if you specify the particle component of the radiation, then you have the universal half scale, universal spectrum, although it is non-equivalent. And this can lead to the universal production of dark matter, baryoleptogenesis, and also the suppressed maximal temperature has some indication of the phase transition and gravitational waves and so on. And basically that's it. Thanks for the attention.
Any question or comment? Please.
Okay, thank you very much for a very nice presentation. So, can you get some constraints on the dark matter from your approach? So, what kind of matter? So, is it weakly interacting massive particle? If it is weakly interacting massive particle, so what is the mass and other things? So, can we get some constraints?
Yeah, thanks. Thanks for asking it. Okay. Yeah, so this interaction vertex is, as I said, it's pretty much like the beam type dark matter model, like assign the Z2 out charge to the dark matter. The lowest order interaction we can write down is this type of interaction, and this is used for the beam paradigm. So this mechanism becomes particularly important when you consider the dark matter mass is larger than the reheating temperature. And previously, people just discussed about this thermal population, thermal distribution, which can exist before the completion of reheating. But however, as I said, there's a universal half-scale-like distribution, and this can provide another production channel, like one of the standard model particle resides in the thermal distribution, the other one is high tail. Then that can be used to generate the dark matter mass whose mass is much greater than this temperature. And if you use that, then this is the certain coupling of the dark matter between the standard model and dark matter. I think we have taken dark matter standard model coupling alpha to the 0.1, for instance. And this horizontal axis is the dark matter mass, and the vertical axis is reheating temperature. And green shaded region corresponds to the previous contribution, like just considering thermal scattering. And this blue shaded region is coming from the thermal and high energy tail scattering. So you can see that typically this dominates over the previous one in the case where your reheating temperature is low and dark matter mass is heavier than the originally more beam model, for instance.
Thank you.
So any other questions? Yeah, please.
So you showed this
You showed this inflaton decay modes to gluon or Higgs
this different decay mode. So, is my question: is there any chance to study this impact on APLHC?
It's really difficult, and I think it's almost not possible. And of course, it depends on the model whether or not your inflaton can have significant coupling to the standard model particles. But particularly in this type of model, or in when this type of preheating and simulation occurs, as I said, the key assumption here is that inflaton couples to the standard model particle very like a gravitational interaction. So such a plug suppressed operator is very hard to test. But however, for instance, you can think about other direction, like for instance, Higgs field itself could be an inflaton. And another thing is that, for instance, dark matter, WIMP dark matter, scalar WIMP dark matter can be an inflaton. In this case, you can directly generate. There is a hope to directly generate the dark matter particle from the collider experiment. But this is completely another direction of the story. So we need relatively large coupling between the standard model particles and the inflaton in this case.
Okay, so last question, final one. Okay, so let me ask one question. So it seems that probably you need some Lagrangian or Hamiltonian to compute this.
Yes.
And all this computation may depend on your model. I mean, how do you introduce the couplings or something like that?
Right.
How much is this universal?
Right, okay. So this universality I have mentioned is what we basically solve is this type of the Boltzmann equation. So the key assumption here is that the radiation or relativistic particle is mostly dominated by the standard model particle. So we just don't consider the other particle like BFT particles. If there is such kind of contribution, we also have to take this effect into account. But suppose that inflaton dominantly decays into the standard model particles, and maybe there is few DOF, few dark matter degree of freedom, but they don't dominate the universe. And under that assumption, I think we can study some reheating and simulation using this Boltzmann type equation. And another theoretical unknown parameter included here is the source time from the inflaton decay. This is completely unknown because we don't know how the inflaton couples to the standard model particles.
Yeah.
And here we just vary the inflaton decay rate and also the branching ratio and how inflaton couples to the standard model particle. We just vary this. But the universality I have mentioned is that this distribution for a fixed inflaton decay rate, we can even change the inflaton decay rate, but as long as the decay rate is very small, then you can factor out the dimensions for parameters, then there is one universal asymptotic behavior in this high energy tail. And this property is actually only determined by the standard model instructions. So they're insensitive to how the inflaton plug in the energy to the standard model species. So that part is actually not, well, you can just factor out that part, and this, for instance, ratio of each individual standard model species are fully determined just by the standard model instructions.
Thank you very much. Let's thank Dr. Mukaida again. And our last speaker is Professor